Hello everyone and welcome to Signals, Systems and Signal Processing with Wolfram U. This lesson will be about methods of solving difference equations. After we mathematically model a discrete time system as a difference equation, we need to solve the difference equation. In this lesson, we give an overview of how to solve ordinary constant coefficient difference equations. We first consider the homogeneous part of the difference equation and solve the equation to get the homogeneous or complementary solution, and then consider the non-homogeneous equation and solve for the particular solution using a method called the method of undetermined coefficients. Once we have these two solutions, we present the total solution as the sum of these two solutions. Let's go over each of these two steps in more detail. For the difference equation, when the right-hand side is 0, we call the equation homogeneous equation. The solution to this homogeneous equation is called homogeneous solution or the complementary solution, denoted by YCN. To find this solution, we simply consider the solution of the form r to the power n and substitute this solution into the homogeneous difference equation. What we get is an algebraic equation that we can simplify as indicated here. This equation is called the characteristic equation, and the n roots of this equation are called the characteristic roots. If the roots are distinct, we write the solution as the sum of exponential terms r1 to the power n to r capital N to the power n. If we have repeated roots, let's say root ri has multiplicity k, then the solution can be modified as shown here with these k terms corresponding to Ri with the exponential coefficients as indicated here. Let's find the complementary solution of the homogeneous difference equation shown here. Using the Wolfram language, we can find the solution. And if we were to find the solution by hand, we consider the solution of the form r to the power n, substitute it into the difference equation to find the values of the base r, which in this case is 2 over 3. Then we can write the complementary solution as shown here. Let's look at another example. Given this second order difference equation, we would like to find the complementary solution. Using the Wolfram language, the solution to the difference equation is found as shown here. Plotting this response for different values of C1 and C2 shows how the solution changes for different values of the initial conditions. Now, solving for the solution by hand, we consider the exponential signal r to the power n and let it satisfy the difference equation, which gives us the characteristic equation and the two distinct characteristic roots as shown here. The complementary solution will be a linear combination of the two exponential terms, which is what we found using the Wolfram language as well. Here's one more example. Let's find the solution to the difference equation given here. We could solve the difference equation using the Wolfram language. The solution is found as shown here, exponential terms with complex coefficients. Now to solve the problem by hand, we replace the y of n by exponential term r to the power n, which gives us the characteristic equation as we have here. And the roots can be found as these two distinct complex conjugate values. This gives us the complementary solution as the expression shown here with complex conjugate coefficients, and this matches the solution obtained using the Wolfram language. The solution can also be expressed in terms of trigonometric functions with magnitude and phase of C1, or also this way with the real and imaginary parts of the complex coefficient C1. As the last example of this section for finding complementary solutions, let's solve the second order difference equation shown here. First, using the Wolfram language, we have -1 to the power n and n times -1 to the power n as the two parts of the solution. Let's see how this is found by hand. Substituting r to the power n into the equation gives the characteristic equation shown here, which gives the repeated characteristic roots of -1. As we mentioned initially, in this case, we write the complementary solution as a linear combination of -1 to the power n and n times -1 to the power n. Now for the second part of this lesson, we consider the non-homogeneous difference equation expressed in the general form shown here. And we find what is called the particular solution, denoted by ypn. The particular solution can be found using a method called the method of undetermined coefficients. Using this method, if the forcing function on the right-hand side of the non-homogeneous difference equation is in one of the forms shown here, exponential, also exponential form with the dependent variable as the base, sinusoidal, product of the two exponential terms shown above, or product of exponential function r to the power n and a sinusoidal, then the solution can be expressed in a similar form as shown here with some undetermined coefficients. We find these coefficients by letting the suggested solution satisfy the difference equation. Finally, using this method, if there are duplicate terms between the particular solution and the homogeneous solution, we'll multiply the particular solution by the lowest power of n that will eliminate the duplication. We will see an example later to show how this is done. First, this simple example, a first-order difference equation with forcing function un, which is constant or a polynomial for positive values of n. So the solution using the method of undetermined coefficients will also be constant with some coefficient, let's say k. We let this solution satisfy the difference equation to find the value of k as 3 here. And so the particular solution is simply equal to 3. Now let's consider the same system with the same difference equation as we just had, but this time with an exponential forcing function, and let's find the particular solution. The particular solution using the method of undetermined coefficients will be an exponential sequence as shown here. We previously found the complementary solution to this difference equation as shown here. And as you can see, we have duplicate solutions. So we rewrite the particular solution as n times the exponential term. Letting this function satisfy the equation, we find the value of k, and the particular solution will then be as shown here. Now that we have seen how we can find the complementary solution and the particular solution, we can write the total solution as the sum of these two solutions. Let's look at one more example, and let's find the step response of the discrete time system modeled by the difference equation shown here with the given initial condition. Using the Wolfram language, we can find the solution. And the solution of this stable first-order system to a unit step input has the shape of a rising exponential that asymptotically approaches a constant value. The total solution is the sum of the homogeneous and the particular solution, which we have found previously. The constant C1 is found by letting this solution satisfy the initial condition. Solving for the constant C1, we get C1 is equal to -2. Therefore, the total solution can be expressed as shown here. In this lesson, we covered the classical methods of finding solutions of homogeneous and non-homogeneous constant coefficient difference equations. We first found the homogeneous solution and then used the method of undetermined coefficients to find the particular solution, and finally expressed the total solution of the non-homogeneous difference equation as the sum of the complementary and the particular solution.